Have you ever wondered how scientists figure out if a new drug actually works or if the results are just, well, random chance? It all boils down to one huge challenge: finding a real, meaningful signal inside a whole lot of noisy, random data. So how do they do it? Let's dive in.
All right, to get our heads around this, let's start with a really practical question. Which brand of gasoline gives you the best mileage? Let's say you've got 4 brands to test: A, B, C, and D. Sounds simple enough, right? Just run some tests, see which one does best, and you're done. Or are you?
Well, not so fast. The real world is messy. So many things can mess with your mileage results. I mean, think about it. The car itself makes a difference, the person driving it, whether the roads are hilly or flat, even the temperature outside or your tire pressure. All these things create a ton of randomness in your data. And that brings us right to the heart of the matter. We have to separate the signal from the noise. The signal, that's the true effect of the gasoline. It's the one thing we actually want to measure. The noise, that's all the other random stuff, all those other factors that are muddying the waters. And the tool that lets us tell them apart, mathematically, is Anova. So how in the world do we start to untangle all of this? Well, it all begins before we even collect a single drop of data. That brings us to our first section: designing a fair test. We've got to learn how to tame that noise right from the start. Here's the crucial idea. Good data doesn't just happen by accident. If you want a clear answer, you can't just go out and collect data randomly. You have to design a proper, thoughtful experiment. This whole concept was really pioneered by a statistician named Sir Ronald A. Fisher, and honestly, it changed the way science gets done. Fisher laid out 3 basic rules for any good experiment. First, you've got randomization. That just means you randomly assign your treatments, in our case, the gasoline brands, so you don't accidentally introduce any bias. Second is replication. You have to repeat each test multiple times. You can't just test each gas once. You need a reliable average. And third, local control. This is all about grouping similar things together to cut down on that background noise. Okay, so those principles sound great on paper, right? But how do we actually apply them to our gasoline problem? We do it by picking a specific experimental design. Now, if everything was perfectly identical, you could use a simple, completely randomized design. If you had just one big source of noise, like different types of cars, you could use a randomized block design, where each car type is a block. But for our problem, we've got 2 big sources of noise to worry about: the different cars and the different drivers. For that, we need something a little more elegant. And this is it. It's called a Latin square design, and it is just a brilliant solution. Just look at the perfect balance here. Each gasoline, A, B, C, and D, gets tested by every single driver and in every single car exactly one time. It's this beautiful structure that makes sure no single brand gets an unfair advantage. Gas A isn't just tested by the most fuel-efficient driver, for instance. Instead, the effects of the different cars and drivers get spread out evenly, basically canceling each other's noise out. It's pretty cool. All right, so we've designed this clever experiment, we've collected all our mileage data, now what? Well, now it's time for the main event. Let's move on to the Anova verdict and actually measure that signal. So what exactly is analysis of variance, Anova? At its heart, it's a method that does exactly what it sounds like. It takes all the variation, all the ups and downs in our data, and it analyzes it by breaking it down into where it came from. I want you to picture all the variation in our mileage data as one big pie. What Anova does is it mathematically slices that pie into 2 really important pieces. The first slice is the variation you see between the different gasoline brands. We can think of this as our potential signal. The other slice is the variation within each brand's own set of tests. That's our random noise. Let's make that crystal clear. The variation between groups is asking, on average, how different was the mileage for gas A versus gas B versus gas C? But the variation within groups is asking something else. It's asking, even when we were just testing gas A over and over, how much did the mileage still jump around randomly? And so this whole complex problem gets boiled down to one single, beautiful question. Is the variation between the groups a lot bigger than the variation within the groups? Or, to put it another way, is our signal a whole lot louder than our background noise? Now, to answer that question, Anova calculates one powerful number. It's called the F statistic, and the easiest way to think about this is that it's just a signal-to-noise ratio. You literally take the variation between the groups and divide it by the variation within the groups. That's it. And here's the best part. The takeaway is super intuitive. If you get a big F statistic, it means your signal is drowning out the noise. It's coming through loud and clear. And that tells you there's a real statistically significant difference somewhere between your gasolines. Your experiment actually found something. But just finding something isn't quite good enough. We need to know what that something is. So that brings us to our final section, pinpointing the winner and what you're supposed to do after you run an Anova. Now, this is a really important point. A big F statistic is kind of like a smoke detector. It goes off and tells you, hey, there's a fire somewhere in the house. It tells you that there's a difference among your gasolines, but it doesn't tell you where the fire is. It doesn't tell you if gas A is the best or if maybe gas C is the worst. To find those specific differences, we have to use something called post hoc tests. Post hoc literally just means after this. So after Anova gives you the green light, these follow-up tests go in and compare every single pair of gasolines to each other. A really common one is called Tukey's Honestly Significant Difference Test, which does exactly what it says. It tells you which pairs have a difference that's, well, honestly significant. So let's just recap the whole playbook here. Step 1, you carefully design a fair test, using a clever structure like a Latin square to control for noise. Step 2, you run Anova to get the big picture verdict. Is there a signal in there or not? And step 3, if the signal is strong enough, you run post hoc tests to zoom in and pinpoint exactly which groups are different from which. And this 3-step process, design, analyze, conclude, it's not just for testing gasoline. This is a cornerstone of modern science, of medicine, of industry. It's used everywhere, from testing new medicines in clinical trials to companies testing different versions of their website to see which one makes more money. It's really just a powerful, methodical way of thinking that lets us cut through all the random chaos of the world and find out what's actually real. So that brings me to a final thought for you. Now that you know the basic framework for finding a true signal in a world full of noise, what questions are you going to start asking?